Hi. In some of the past lectures, we've spoken about how important it is that the series we're dealing with all have positive terms. And the test we're going to be discussing today applies to a special kind of series that doesn't have only positive terms. Those are called alternating series. In particular, when the sign always switches off, it's an alternating series. So if you can write an alternating series can be written as the sum of an is really the sum of minus 1 to the n bn, where n goes from 1 to infinity. And what happens when n is odd is that minus 1 to the n is negative. When n is even, minus 1 to the n is positive. And these bn's will be greater than or equal to 0. So a couple of examples of this would be, for instance, 1 minus a half plus a quarter minus an eighth plus 1/16, because I could write this as the sum of minus 1 to the n plus 1, because we start with a positive term, so we'll want the power of the first of the n equals 1 term to be even, of 1 over 2 to the n minus 1. Okay. You could also start the indexing at 0, and then it would be something like this. N equals 1 to infinity, n equals, 0 to infinity of minus 1 to the n times 1 over 2 to the n. Okay, you just want to check that whatever formula you use, that the starting index lines up with the starting term. Okay, and in either of these cases, even though the exponent is a little different, we have a positive term being multiplied by negative 1 to n, or n plus 1. Okay? Another example would be 1 minus 2 plus 4 minus 8 plus 16. You probably have a sense that this is going to be a divergent series, and you're very much correct in that. But it is still an alternating series, because we can write it as minus 1 to the n plus 1 times 2 to the n minus 1. Okay. Same idea, except this time it's powers of 2 rather than powers of a half. Okay, those are two examples of alternating series. And alternating series have a really special convergence properties. They have a test that you can apply to them. We'll switch to a separate color for that. The alternating series test or the AST is as follows. If you have an alternating series, minus 1 to the n b sub n, where n goes from 1 to infinity, okay, and the same applies for minus 1 to the n plus 1, or n minus 1, where bn is greater than 0, then if, first off, bn is steadily decreasing, so bn is greater than or equal to bn plus 1, and the limit as n goes to infinity of b sub n equals 0, then the series converges. Okay. So those are two pretty weak conditions, right? As long as you have a decreasing sequence, it's going towards 0, then the alternating series associated to those terms is convergent. That's pretty powerful. So let's take a quick look at the proof. We won't focus too much on that, but we just want to get the example, to get the idea. So the idea is we want to consider the sequence of odd and even partial sums separately. Okay? So when we do that, for instance, we have S2 is equal to B1 minus B2. Okay? S4 is equal to B1 minus B2 plus B3 minus B4. Okay? So what we'll notice about each of these, and the same is true for all subsequent even partial sums, is that since B1 is greater than or equal to B2, we know that S2 must be positive. Okay? The partial sum there must be positive. And let's actually make this a strict inequality. So B1 is strictly greater than B2, so S2 is positive. Well, S4 is equal to that one is just S2, and then we're adding B3 minus B4, which is also positive. So this must be greater than S2. So then that means that we have an increasing sequence. S2 less than S4, less than S6, etc. Okay, so the even partial sums are an increasing sequence. But when we consider it in a bit of a different way, if we take S2n, instead of splitting it up with the first two together and the second two, let's pull out the first one and then take the next two and group them together. What we'll notice here is that the first term is positive, but then all of the other terms, you're subtracting positive terms, right? Because we know that B2 minus B3, B2 is bigger than B3, so that's going to be positive. This is also going to be positive. All of these terms are going to be positive, including this one. So this has to be strictly less than B1. Okay? So the even partial sums are monotone increasing. And they're bounded. Okay, and we have a sequence, we have a theorem that says that a monotone bounded sequence is converges to a limit. Okay, and that would mean if we know that all of the partial sums converge to the same limit, then that's great. That means the series converges, but we have to check the odd partial sums. So odd partial sums S2n plus 1. Well, this is equal to S2n plus B2n plus 1, right? That's just the next term in the sequence, and the odd indices are all positive. Well, if I take the limit of both sides of these equations as n goes off to infinity, what I'll find is that from above, we know this converges. And we know by the conditions that we put in the test, this is 0. So if you have a convergent sequence and you add 0, that converges to the same limit. Therefore, the left-hand side also converges. Okay. That's the idea of the proof, but let's see it in action. Let's consider the following example. If we have the sum of minus 1 to the n divided by n, where n goes from 1 to infinity, can we determine if this is convergent or divergent? Well, looking at this sequence, I can see that this is clearly an alternating series. Okay, so this is an alternating series with Bn equals 1 over n. Okay, so let's apply the alternating series test. Alternating series test says that if, first off, Bn is greater than Bn plus 1, and indeed 1 over n is greater than 1 over n plus 1, because when the denominator is smaller, the fraction is bigger. Okay? How about limit as n approaches infinity of Bn equals 0? Well, if we take the limit as n goes to infinity of 1 over n, this sequence certainly converges to 0, right? Because as n gets really big, this fraction gets really small, approaching 0. So, by the alternating series test, the series converges. So that's quite simple. And this, by the way, is called the alternating harmonic series. Unlike its cousin, the harmonic series, which diverges, this one converges. And that's the power of the alternating factor here. Okay. Let's look at another example. Oops. Example. If we take sum from n equals 1 to infinity of minus 1 divided by ln n, is this convergent or divergent? Okay. Well, here you have to be careful. Just because you have a minus 1 in here does not mean the alternating series test applies. So this series actually is not alternating. Oh, actually, I need to start this at 2. It's undefined at n equals 1. But these terms are all negative. So we would have to apply a different test. We would have to apply perhaps the comparison test. So we could apply the comparison test with 1 over n. We know this diverges. So clearly the comparison test only really applies when the terms are all positive. But what we could do is we could say, look, this series S equals n equals 2 to infinity of minus 1 over ln n. This is really just minus the series 1 over ln n. And so we can determine the convergence of this series and then apply the minus sign. Okay. So let's determine this. So this series we know, with this series we can apply the comparison test to. So note that ln n is less than n, and that means 1 over ln n is greater than 1 over n. And since the terms of this series are greater than the terms of this series, and this is divergent, so by the comparison test, one over ln n diverges, which implies that the minus of that also does. Okay. Sometimes it won't be so clear from the series that you're looking at that it's alternating. So here's an example. If we take the sum of sine n plus 1/2 pi divided by 1 plus the square root of n, where n goes from 1 to infinity. So let's take a look at the first few terms of this series. Well, we have, for n equals 1, we have sine 3 pi over 2 divided by 1 plus square root of 1. So what's sine 3 pi over 2? Sine pi over 2 is 1. Sine 3 pi over 2 is minus 1. So we have minus 1 divided by 2. Okay, the next term in the series is we have 2 plus 1/2, so that's 5/2 pi. And that's going to be, sine of 5/2 pi is positive 1. So then we have 1 over 1 plus square root of 2. Minus, or rather, Let's give it plus. We're not sure yet. So the next one is n equals 3. So we have sine 7/2 pi. Sine 7/2 pi is minus again. 1 plus the square root of 3. And indeed, this will be an alternating series. So this can be thought of as truly n equals 1 to infinity of minus 1 to the n divided by 1 plus root n. Okay. And once we see that this is an alternating series, because the rest of the term is positive, so this is alternating, then we can apply the alternating series test. Okay, once again, we just need first bn is greater than, strictly greater than, bn plus 1, and indeed 1 over 1 plus root n is greater than 1 over 1 plus root n plus 1, based on the fact that this denominator is larger. Okay, then we need to check that the limit as n goes to infinity of 1 over 1 plus square root of n is 0. And indeed, this is true. Okay, you can see that the denominator goes to infinity as n goes to infinity, so the fraction goes to 0. So by the alternating series test, the series converges. Before we close off, I want to talk about another concept which comes up in the next section but is closely related to this. So those notions are conditional convergence and absolute convergence. So if a series converges, so suppose that an is a series, okay? Let's say it's a convergent series. If the sum of the absolute value of an, so taking all of your terms and throwing away negative signs, if this also converges, then we say the sum of an is absolutely convergent. Okay. So you can think of that as being, it converges even as an absolute value. So it's absolutely convergent. If, on the other hand, the series of absolute values diverges, then the series an, which converged, is said to be conditionally convergent. Okay, it converges, but only on the condition that you keep these minuses and pluses that cancel each other out. Once I take absolute values so that all of your terms add up in the same positive direction, then it diverges. Okay? So, we saw a few examples already. So, for instance, if I take the sum when n equals 1 to infinity of minus 1 to the n over n, I saw before that this converges by the alternating series test. Right? However, if I were to take the absolute values, okay, absolute value sum from n equals 1 to infinity of the absolute value of that, which is just 1 over n, this is the harmonic series which diverges. So, the original sum is conditionally convergent. Let's look at another example. If we have the series sum from n equals 1 to infinity of minus 1 to the n divided by n squared, I could use the alternating series test to verify that it converges. Okay, but I could also just say, let's take the absolute value that is given by 1 over n squared, which converges. And an important theorem is that if a series of absolute values converges, then so does the original series. So I don't even have to apply the alternating series test. I can just say, well, the absolute values converge, so the original series converge as well. Converges absolutely. Okay. Just to be clear about this point, what this is saying is absolute convergence implies convergence, but not the other way around. Convergence does not imply absolute convergence. Convergence, absolute convergence implies convergence, not vice versa. Okay, I think that's it for today. Thank you very much.